Recitation weekly worksheet number 8 is the last worksheet that we work together, and it covers the PV work and the enthalpy, different ways of enthalpy, basically calorimetry and this worksheet, and I included some Hess's law and standard enthalpy of formation in the exam review file. So as always, don't forget to write your name and student ID. And the first question, if a balloon is inflated from 0.1 liter to 0.85 liter against an external pressure of 1 atmosphere, how much is the work? And it wants to work in joules, so you write down the information that the question is giving you. So you have pressure, you have volume, initial volume and final volumes, and work is negative P delta V, so it's negative 1 atmosphere V2 minus V1, and you get negative 1.75. What is the unit? The unit is liter atmosphere. The question is asking the work in joules, so you have to do a conversion. So 1 liter atmosphere is 101.325 joules, so you do the conversion, and the amount of work in joules is negative 177 joules. The second question, the temperature of an object increases. When it says increases, it means that's the delta. It's not T1 or T2. It increases by 29 degrees Celsius, so that's delta. And since it's increasing, so it's plus sign, so it's positive 29 degrees Celsius, and that's delta T. You write it down on the left. And when it absorbs 3693 joules, so it absorbed the heat, so the heat is positive, right? So Q is positive 3693 joules. Calculate the heat capacity. So I talked about the difference between heat capacity and a specific heat capacity. So heat capacity could be for any amount of mass, but a specific heat capacity is for just a gram by 1 degree Celsius. So if you have heat capacity, the Q is C delta T. There's no M in it. So to find the heat capacity, C is Q over delta T, and you just plug in the numbers and get the heat capacity, which is 127, and the unit is joule per degree Celsius. So if we have the same object, and if we know the mass of it, we know it's 331 grams. Now, what is specific heat capacity? Well, if you have a specific heat, if you want the specific heat capacity, you have to use QMCAT. So to find the specific heat capacity, you have Q and you have delta T. Now you have M, so you plug it in and you find the specific heat capacity, and the unit is joule over gram per degrees Celsius. Okay, the third question. At constant volume, the heat of combustion of a particular compound is negative 3952.0 kilojoule per mole. Okay, so that's a heat of combustion and it's per mole. So when we say per mole, it's delta H of the reaction. Okay, so I write it down on the left as delta H of the reaction, and so when 1.211 gram of this compound, so you have the mass of the solute, so the mass is 1.211 gram, and you also have the molar mass here. Write it down. You see, when you write the information on the left, when you summarize the information, you just write down a list of them. It makes it easier to just have an overview what we have and where we want to go. Okay. So we have the mass and molecular weight of the molar mass and molecular weight of the solute. Well, it's not a solute, it's just a compound. So the compound was burned in a bomb calorimeter. The temperature of the calorimeter increased, including the content. So everything inside the calorimeter, if you have a solution, the calorimeter, metal, and everything, has the temperature rose by 4.453. So that's a delta T, and that's for calorimeter. what is the heat capacity of the calorimeter? So I told you that usually for calorimeters we use heat capacity because there are multiple contents in it. It has the metal walls, it might have some solution in it, some other stuff in it that we don't need to go into detail and see what is the specific heat of this compound, of that compound, and then what is the mass of each. So instead, they just give us the specific heat that include the mass and everything of the calorimeter. Okay, that makes it easier. So so what happens? So whatever heat that the reaction is giving off, the calorimeter absorbs it, right? And we are monitoring the temperature of the calorimeter. So with just a negative sign. So one of them is giving off heat, one of them is absorbing heat. So the sign is different. So first you want to find how much energy was released from burning that compound. So we know the enthalpy, and the enthalpy is per mole, but we don't have a whole mole. We just had 1.211 gram of the compound. Okay, so to find the amount of energy, we start with the mass of the compound. You do some conversions. So you have the molar mass, you have to convert the mass to mole, and then you have this enthalpy. We've learned this in thermochemical equation. So the enthalpy, you can relate the kilojoule or joule to the mole. So you can go from mole to joule or kilojoule. So we know that the amount of heat for that specific amount mass of the compound. So we had negative 36.79 kilojoule as Q of the reaction. So Q of the reaction is equal with a negative sign to Q of the calorimeter, right? So QCal equal negative Q reaction. So QCal is positive 36.79 kilojoule. And for QCal, we have Ccal delta T. That's the equation that you have to memorize. For if you have heat capacity, it's C delta T. If it's specific heat capacity, it's MC delta T. For calorimeter, always we have C. We have capital C, the heat capacity. So for calorimeter, it's C delta T. And to find the the heat capacity of the calorimeter, it's QCal divided by delta T. And you just plug in the numbers and find the heat capacity of the calorimeter. Question number 4 was a duplicate. So, and I was already into the first page, so I didn't want to erase that and then start over. So just keep it like that. So question 4 is a duplicate. Question 5, let me zoom in. Okay. So question 5, a researcher studying the nutritional value of a new candy places a 5.7 gram sample of the candy. Okay, so you write down the mass. The mass is 5.7 inside a bomb calorimeter and combusted in excess oxygen. The observed temperature increased by 2.61. So it says the temperature increased by, so that's delta. It's not T1 or T2. So delta T is 2.61 degrees Celsius. If the heat capacity of the calorimeter, so Ccal, is 41.7 kilojoule per degree Celsius. So we see it's not specific heat. You can even see it with the units, right? If it was a specific heat, it was kilojoule per gram per degree Celsius, right? And as I said, for calorimeter, we always have heat capacity. We never use specific heat for calorimeter. Okay, so how many nutritional calories are there per gram of candy? Okay, so for the reaction, for the combustion reaction that happened, so we have the energy coming off the reaction and going into the calorimeter, right? So Q of the reaction equal the negative QCal. And we can find the QCal by C of the calorimeter times the delta T. So negative C cal delta T, you plug in the numbers and you get the Q for the reaction. And that reaction, that amount of heat was released uh, with 5.7 gram of candy. Okay, what we are trying to find is the calories per gram, so you have to divide it by the total mass. Okay, so we find the Q of reaction here, and we have to divide that by the total mass of a candy, which is 5.7. So we do that, but the question is asking calories per gram, not kilojoule per gram. So you have to do one conversion. 4.184 kilojoule is one calorie, and you do the conversion and you get 4.56 calorie per gram. Question number 6. You have oops. So you have coffee cup calorimeter, and it was used to heat a solution, to measure the heat of a solution. So the change in enthalpy that occurs when a solid dissolves in water. Okay, what happens that when you dissolve water, you might release or absorb heat. Okay, so they were using the coffee cup calorimeter to do that. So they used 10 gram of the sample. So you write down M of the solid or the solute. 10 gram of this ionic compound with a molar mass of 130. So you have the molar mass, you write it down. Was added to a sample of deionized of DI water to produce 60 gram of solution. So this is the mass of solution. That's really important, okay? Not the mass of water. That's the mass of solution. So the mass of solution is 60 gram. And after stirring the solution and the solid dissolved, the temperature was found to change from 25 to 23. So you have to be careful which one is the initial and which one is the final. So the T1 or Ti is 25 and T2 or Tf is 23.7. Okay. Calculate the enthalpy of solution. We want the delta H. Okay. Per mole. So we want it per each mole. Okay. So we first find the Q of the reaction, which is for this 10 gram that we dissolved. Then you have to divide it by the mass and then convert that to mole to find the delta H. Delta H is the amount of heat per each mole. So what do we have? It's also in the end you have some extra information. You have the specific heat of the solution and you have heat capacity of the calorimeter. So this is your calorimeter. Here you have the calorimeter. So you have a container, you have a solution, and you have your solid that's dissolving into the solvent. Okay, so the dissolution of the solid is going to make or absorb or release some heat, so that's one Q. The solution is going to absorb or release the heat or give off the heat, so you have the Q for the solution, and the calorimeter itself can absorb or release heat, so you have the Q of the cal. So in some question they say that you can neglect the amount of heat, the heat loss to the surrounding, so in that case we consider the Q cal as 0, but that's not always the case. So if you have information for the calorimeter, it means you have to include the calorimeter. So basically in the calorimetry questions, you write down any Q that might happen in the calorimeter, and the sum of all of them should be 0. Okay, so you have Q of the reaction, you have Q cal, and you have Q of solution, and they're all equal to 0. So what we're trying to find is Q of the reaction, which is the dissolution of the solid into the solvent. Okay, it's dissolving the salt in the solvent. That's our reaction. So, and we're just taking these two terms on the other side of the equality. So it's minus the sum of Q cal and Q of solution. We can find Q cal by C cal times delta T Also, we can find the Q of the solution by the mass of solution times the specific heat of solution times delta T. So we have all of those components. We have the C-cal, heat capacity of the calorimeter. We have delta T, so you plug that. You have the mass of the solution. You have to be careful with that. We have mass of the solid and mass of solution. And for solution, you have to use the M of solution, which is 60 gram. So you plug that, and you have specific heat, and you have delta T. You plug all those numbers, and what you get, if you're careful with the units, the delta T is a negative delta T because T2 is smaller than T1. So you have to be careful with that. And then you have a negative here, so take everything into account. In the end, what you get for the Q of the reaction is a positive number, positive sign, and the amount is 336 joule. Okay, so that's the Q of the reaction. What we want is the delta H of the reaction, so we want it per mole. So you have to divide it by your total mass first. So we have 10 gram of the solid, and that mass is the mass of the solid that you're dissolving, okay? Because that's where this heat come from, by dissociation of the bonds of that solid, okay? So you dissolve it in, so you divide it by the mass of the solute, which is 10 gram, but that would be joule per gram, but delta H is joule or kilojoule per mole. Okay, so you have to convert that to mole. So you use the molar mass of that solid, and that's given is 130 gram per mole. So you apply that, you do that conversion, and what you get in the end is 4.36 times 10 to the third joule per mole. Okay, the last question. So we have a solid, and we have the molar mass. So the molar mass of the solid is 61.6. In constant pressure calorimeter, we have this mass, 18.3 gram of the compound, dissolved in 383 gram of water. You see, this is the thing that you have to be careful. This is the mass of water, not the solution. This is the mass of the solute. Okay, so if you want to find the Q of the solution, you have to add these two because it's solution, it's solute and solvent. So you have to add these two together. So I just write down the information first. So the mass of water or the solvent is 383 gram at 23 degrees Celsius. So that's our initial temperature, that's T1. The temperature of the resulting solution rises to 29.1. So the T2 is 29.1. And we assume that the solution has the same specific heat as water. So the C of the solution, I didn't have enough space over there, so I write it here. So the specific heat of the solution is 4.18. And there is negligible heat loss to the surrounding. So that's one of the things I mentioned in the question 5, I guess, or maybe 6. So since there's negligible heat loss to the surrounding, and that included calorimeter 2, so QCal equal to 0. So part A is asking how much heat was absorbed by the solution. So it's easy to find the Q of the solution. It's MC delta T, MCAT, okay? But you have to be careful. That's the mass of the solution. So you have to add these two mass, the solute and the solvent. That's the mass of the solution. You have the C of the solution, and you have delta T, so you just plug in and find the Q of the solution. In part B, it's asking the enthalpy of the reaction, okay? So what you have in the calorimeter, you have the reaction, you have the solution, and you have the calorimeter. So the question says, assume that the calorimeter doesn't absorb that much of heat, so it's almost 0. Or if there is no information about a calorimeter in the question, then you don't need to worry about that. Okay, if you have information about a calorimeter, you have to include a calorimeter. Okay, so that is 0, so we don't need to worry about that. So Q of the reaction equal negative Q of the solution. and we already found Q of the solution in part A, so we have the number. So it's asking for the enthalpy. Enthalpy, as we said, is per mole of the solute, of the solid. So first we have to divide the Q of the reaction by the total mass of the solvent, of the, solute, of the solid, and then we have to convert that by the molar mass to number of moles of the solute. And what you get here is joule per mole, and that's the enthalpy. So the enthalpy, I just convert that into joule, into kilojoule, is 34.5 kilojoule per mole, and that's our enthalpy.